So last part I left at this topic. We were about to start the relation. Okay, so let us start with the definition. Let A and B be two sets. Okay, A is a set and B is a set. Then a subset of A cross B is called a binary relation or just a relation from A to B. Okay, so now suppose A is 1, 2 and B is 3, 4. So the what A cross B will be 1, comma 3, 1, comma 4, 2, comma 3, 2, comma 4. So four elements will be there. So any subset among these four elements, okay, four what to say pairs, that will be a relation from A to B. So thus, if R is a relation from A to B, then R is a set of ordered pairs A comma B, where A belongs to A and B belongs to B, capital B. And conversely, if R is a set of ordered pair A comma B, where A belongs to capital A and B belongs to capital B, then R is a relation from A to B. And that's just a definition. Okay, they might ask sometimes. So if A comma B belongs to R, we say that A is related to B by R, capital R. The R is nothing but the relation. Okay, this is denoted by A capital R B. A relates B, which means A is related to B by R, so A relates B. If R is a relation from A to A itself, that is, R is a subset of A cross A. So how will you write a subset of A cross nothing but suppose 1 comma 2 is there. So A cross A is nothing but 1 comma 1, 1 comma 2, then 2 comma 1, 2 comma 2. Okay, 2 comma 1, 2 comma 2. So like this you will have that A cross subset. We say that R is a binary relation on A. So we have an example, set A is 0, 1, 2, set B is 3, 4, 5. Let R be relation 1, comma 3, 2, comma 4, 2, comma 5. Okay, so 1 is related to 3 by a relation R. So 1 is related to 3. Then 2 is related to 4. Then 2 is related to 5. Okay, so R is subset of A cross B. This is represented by a diagram. So this from this diagram, okay, it is related here. And the diagram is called the arrow diagram. This diagram is what arrow diagram. You will be like, where is arrow? It's not there. Just put it off, no problem. Note, if A has m elements and B has n elements, the number of relations from A to B is 2 power m into 1. See, A has three relations, so three elements. B has three elements. So number of relations I can do is 2 to the power of m into n. That is 2 to the power of, for this thing, 3 into 3, that is 9. How come it is 9? So see here, from 1 0 I can send to all these 3. Then similarly from 1 I can send to all these 3. Similarly from 2 I can send to all these 3. So from 0 3, from 1 3, from 2 3 times. So 3 3 3, that is 9. Okay, 2 to the power of mn elements. That is oh my god. Okay, this is the definition. 2 to the power of mn relations are there from A to B. Okay, let me just erase this. Okay, so let us see a problem. This thing, don't get confused. Okay, just trying to explain something, but 2 to the power of 9 goes way, a lot of numbers are there. Okay, so from A to B. Okay, so yeah, let us move on. Let A is equals to 1 2 3 4 5 6 and R be the relation on A defined by A comma B belongs to R. If and only if A is a multiple of B. So now I can A comma B is a ordered pair. Okay, so now what I can do, I can make a relation from this A comma B such that only if and only if A is a multiple of B. For example, uh, 4 4 is a multiple of 2. Similarly, 6 is a multiple of 3 and 2. 3, okay, multiple of 3, 3 2s are 6, then multiple of 2, 2 3 times. Okay, like that it is. Write down R as a set of ordered pair now. Now what they have said, they have a solution. R is a, so let our relation R be like a set of ordered pair A comma B such that A comma B belongs to A itself and A is a multiple of B. Okay, so now see here, similarly, a very simple thing I'll tell you what you have to do. First, 1 you have to take, you have to, 1 is multiple of 1 itself. So I'll write 1 comma 1. Now I'm taking 2. So 2 is multiple of 1 and then itself. So 2 is multiple of 1 and 2 is multiple of itself. Similarly 3 is multiple of 1. Every letter is multiple of 1. And since it is odd number 3, I cannot use 2. It is not multiple of 2. So 3, 1 and 3 itself. 3 comma 1, 3 comma 3. Then I will take 4. 4 is multiple of 1, 4 is multiple of 2, then 4 is multiple of itself. 4 comma 1, 4 comma 2, 4 comma 4. Similarly, 6 is a multiple of 1, 6 is a multiple of 2, 6 is a multiple of 3, and then 6 is multiple of itself. 6 comma 1, 6 comma 2, 6 comma 3, 6 comma 6. So this is my answer. The second question, if a comma b, let a comma b be a finite set with mod b is equal to 3. If there are 4096 relations from a to b, what is mod a? Okay, in the beginning of lecture, in the previous video, where I was explaining that Cartesian product, I had set this formula, right? So given mod a is equals to m, mod a is equals to m, okay, and mod b is equals to n. This formula, then there are 2 power m into n relations from a to b. Given b is equals to n, that is equals to 3, and 2 power mn is equals to 4096. I can substitute the value of n, that is 3. So 2 power 3 into m is equals to 4096. Now what I can do, I can take log. When I take log here, okay, see here, ignore this text part. I just try to solve it in different way. Even though if you solve like this, we'll get the same answer. Don't worry. Let us solve like this. So now see here, 2 power 3m is equals to 4006. So I can take log here. So here there is a formula, basic formula, log to the power of m, log m to the power of n is equals to n log m. Okay, this is the formula. So here I have log 2 to the power of 3m is equals to 3m into log to the base e 2. Similarly, log to the base e 4096. Okay, then what I can do? M I am keeping as it is, and 3 into log e to the power of 2 I am sending to the denominator of this. Okay, now don't be so nice and just cancel this and this. That's foolish. Okay, I am not going to cancel log and log here. Okay, this is not e power 2, this is log e 2. Okay, log suffix e then 2. So find the value of log to the base e 4096. I think log to the base e is nothing but ln. Okay, you have to take ln in your calculator. Ln 4096 divided by put the bracket, or same take in scientific calculator, you can actually write like this, right? That what to say, fraction type thing, and then keep this in the denominator. You will get this value. Okay, if you take by log, I think you might get some different value. So you have to take ln here. Okay, log to the base e is nothing but ln. Thus mod a is equals to 4. Okay, now this is a question. So let us see another question in this. Let a be a set 1 comma 2 comma 3 and b be a set 2 comma 4 comma 5. So it is saying to determine the following. Then what I have to, find a cross b. You know how to find a cross b, right? A cross b, mod of a cross b. So if they had said only a cross b in like this, okay, then you have to write the pairs 1 comma 2, 1 comma 4, 1 comma 5. Actually also, if not, you can simply say how many number of relations that can be is m into n, that is 9. Just write it off. 1 comma 2, 1 comma 4, 1 comma 5, 2 comma 2, 2 comma 4, 2 comma 5, 3 comma 2, 3 comma 4, 3 comma 5. Just write how many 9 are there, right? A mod m is 3, mod b is n 3. So total number of ordered pairs are 9. But how many relations you can do from this is 2 to the power of mn. How many number of pairs you can remove is mn. How many number of relations you can remove is 2 power mn. Okay, then number of relations from a to b. Okay, number of relations, see same now. Number of relations from a to b is 2 power m into n is equal to 2 power 9 is equal to 512. Third question, number of binary relations on a. Binary relations on a is nothing but from a cross a. Okay, in the beginning we have seen the definition, right? So if I have to take number of relations from a cross a, so I will take mod a into mod a, 2 to the power of mod a into mod a. What is mod a? That is m, that is 3. So I will take 2 to the power of m into m, that is nothing but m square, that is what 3 3 is a 9, again 9 square. Okay, I will get same answer. Okay, then fourth one, number of relations from a to b that contains 1 comma 2 and 1 comma 5. So number of variations on, okay, that is fourth question, right? Yeah, let r1 is equals to 1 comma 2 and 1 comma 5. Every relation from a to b that contains the element 1 comma 2 and 1 comma 5 is in the form of r1 union r2, where, okay, where r2 is a subset of r1 in a cross b. Okay, so see here, now we will get one relation. Okay, from a to b, suppose we got one relation, that is r1 we are saying, and another relation we got r2. Suppose this okay, where here r1 is this thing. So now what you're saying, from A cross B, what we'll take, we'll say that this R2 is a subset of this itself. Okay. Now number of such relations equals to number of subsets of R1 complement. Now okay, so if R1 is this, okay, R1 is this, then complement of R1 will be all the number of pairs except this two. Okay, complement is that itself, right? So 2 to the power of 7 into that is equals to 2 to the power of 7. How it is 2 to the power of 7, nothing but here we have, okay, since you see here they have written here, since R1 complement should be equal to A cross B minus R1, that is equals to 9 minus 2, which is equals to 7. How we got 2 is nothing but R1, okay, in question itself they have given us, right? It should be 1 comma 2 and 1 comma 5. So R1 has two elements, that is mod R1 we can write 2. Since how we have said here, A has three elements, 1, 2, 3. See, since this is in bracket, this whole thing is one element, this whole is another element, so two elements are there. So to find the number of, okay, that contains 1 comma 2 and 1 comma 5, I can simply say that among all the relations, all the ordered pairs I have, so I will take complement of this thing. If I take complement of this thing, then I'll get, I can write it as A cross B, okay, set of A cross B minus R1. In previous sum we had seen that uh, this set minus this set, only the which is common only will get minus. Okay, here we are not they are not asking to write all those sets. They are not asking. What they are asking, how many number of sets will be there. So in above we had seen one question in that Cartesian product. If I do subtract, so what will happen? This will be having suppose 9 elements. So here I will have suppose 9 elements are there. So here, how many elements are there? The same elements in this two. Suppose, okay, here also I had this 1 comma 2 and 1 comma 5, and here I had suppose 9 elements, and I had, okay, but here actually I have 2 itself. So I have here also 1 comma 2, 1 comma 5, including 1 comma to 1 comma 5. I have 7 other remaining things. So if I take this set minus this set, so obviously same terms won't be repeated. Even if it is having some other terms and all, some other terms is there, that won't affect anything, because only same terms from the set will get minus, so only 7 will remain. Okay, so 2 to the power of, so remaining elements are 7. That's why I'll take relations, so many relations it has asked. So 2 to the power of 7, that is 128. Don't worry how you will remember. In exam they'll ask same itself. Might be what they might do. They might change this number. They might give only one here, or they might give only they might give more than one. If they are giving one, then only here 9 minus 1 will happen. If you are giving 3, then 9 minus 3. So what is the remaining resultant answer? 2 to the power of that answer is your answer. Fifth one, number of relations from A to B that contains exactly 5 ordered pairs. Okay. Since A cross B contains 9 ordered pairs, the number of relations from A to B that contain exactly 5 ordered pairs is equal to number of ways of choosing 5 ordered pairs from 9 ordered pairs. This number is 9C5. See here, total numbers I have 9. Don't forget that all the concepts of this module can be asked in different topics also. So what he has asked here, fifth question, number of relations of A to B that contains exactly 5 ordered pairs. So total ordered pairs, how many are there? It is 9. So 5 out of 9. Whenever in your mind it comes 5, 5 out of 9 pairs, then simply take 9C5. Okay, that is what is a combination. 126 is your answer. Then last, number of binary relations on A that contains at least 7 ordered pairs. So if it is at least 7, then less than or equal to, sorry, greater than or equal to 7. Okay, greater than or equal to 7. So it will be till 9. So 7, 8, 9. If same way, if you are using combination, so it will be 9C7, 9C8 plus 9C9. See, same thing. Whatever the following answers is, just add it and make it up. Now we have matrix of a relation. Consider the set A is equals to A1 comma A2 so on up to AM, and B is set B1 comma B2 so on up to Bn of order m cross n respectively. Then A cross B contains all the ordered pairs of the form AI comma Bj where I 1 is less than equals to I less than equals to m, and similarly 1 is less than equals to j less than equals to n. In the sense, ai will be I is from the range 1 to m, and j is of the range 1 to n. Okay, that's what it means, which are mn in number, m into n in number. Okay, so 1 to m and 1 to n, if I have to add, so I'll just multiply m and n. Let R be a relation from A to B, so that R is a subset of A cross B. Okay, if R is a relation from A to B, uh, A cross B or A to B, R defines relation A to B. Okay, set let M of ij is equals to AI comma Bj, and say the value of mi if it will be equals to 1 if ai comma bj belongs to R, else 0 if ai comma bj does not belongs to R. R is nothing but the relation from A to B. Okay, it can be any number, so in the resulting set, so for example it can also be two numbers, right? So if you are taking relation from A to B, so it will be in the form of A comma B. So AI comma Bj, same way here. This two, if this pair is belongs to R, I'll write 1. If it is not belongs to R, I'll write 0. So the M cross N matrix found by M of I comma Mij is called the relational matrix for R, or the adjacency matrix, or 0 1 matrix for R. See, you know that in ADA we had that adjacency matrix that wherever there is path, we'll write 1. If there is no path, I'll simply write 0. Like that here. If the number belongs to, if the pair belongs to the relation, I'll write 1. If it does not belong, I'll write 0. Okay, and that matrix is denoted by m suffix r or m of r. Okay, rows of mr, okay, has this 0 to 0 1 matrix corresponds to the element of A, and column corresponds to the element of B. That's the order of matrix, right? This is m cross n and m, and B is n cross n. Then okay, rows will be number of m's and columns will be number of n's, like that they are saying. Okay, when B is equals to A, both the matrices are equal, then MR is an n cross n matrix whose elements are m of ij is equals to 1 if same way A of ij belongs to R, 0 if A is not. Okay, example. Now we'll understand with an example. A is equals to 1 comma 2 comma 3 comma 4. B is equals to 4 comma 5, that's it. So, and the relation they have given 1 comma 4 2 comma 5. So from this only the relation we are taking is 1 2 4 and 2 2 5. This you can understand easily when this kind of diagram is there. Okay, only so 1 2 3 4, right? And here 4 5, 1 to 4 2 to 5. Only this much is the relation we are taking. Many will come, but this relation is defined in the given question. So now see here, where is 1 comma 4? This is 1 comma 4. Where is 2 comma 5? This is 2 comma 5. Only this place I'll write 1, remaining all are zeros. Similarly, A is P comma Q comma R, and they have not given B, they have given only directly R, P comma P, P comma Q, R comma R, R comma Q. So this is nothing but A cross A. So here also PQR, here also PQR I'll take. So see P comma P, P comma P I'll write like that, and P comma Q. So that's it. Then R comma R, R comma R, then R comma Q. Similarly, R comma Q. Only these four places I'll have one coordinates. These four I'll take it as coordinates, only one. Remaining all will be 0. Then diagraph of a relation. So now let us read this definition. Let R be a relation on a finite set A. To get the diagram of R, we follow the following procedure. Okay, you understood, right? At R be a relation on finite set A. To get a diagram of R, we follow the okay. There is a set R. If only one set they have taken name, so there is nothing but A cross A matrix. Okay, so draw a small circle or bubble for each of the element of A and label it with the corresponding elements of A. So suppose A is having 1 2 3, so I'll write 1 2 3 like this. Okay, these circles are called vertices or nodes, so it will become nodes. Draw an arrow called an edge from a vertex x to a vertex y if and only if x comma y belongs to R. Very simple thing, right? In a diagraph, a vertex from which an edge leaves is called the origin or the source for that edge, and a vertex where the edge ends is called the terminus. So you can simply say that what to say infix to say origin, okay, or something that word is there. I'm not able to just spell it out. It comes under your DSA also, in also ADA also. In order in something they say, okay, in and something or something out, some in out something it is, I am not remembering, okay. So a vertex is neither a source or not a terminal. What is an edge known as isolated vertex, and means like this from both the sides. I think it's like that. An edge for which the source and the terminus are one and the same is called loop. For example, node 1 is there, okay, like this it is. So origin for this node is also 1, and terminating terminus is also 1. The number of edges terminating at a vertex is called, sorry, this was I was saying, in degree, and what is the number of edges leaving from this edge node is called out degree. This is the easiest concept. I'll just explain it off. You see, I have a set a comma b comma c comma d, and I have a relation a comma b comma b, d d to b, c to c comma b, c comma d, d comma a, d comma c, which means a comma b means there is an edge from a to b, a to b. Okay, suppose for example, let me just draw it and construct. Okay, so this is a, b, c. I'm using mouse, so I cannot write that neatly. I try to cooperate. So a to b I have 1, then b to b itself, so 1 self, then b to d I have, okay, like this, then c to b, c to b, then c to d also I have, d to a I have, then d to c I have, okay, that's it. Now see here, how many nodes are going out from C? Two nodes are, so two, how many edges are going out of C? That is two edges. So out degree of C is 2. How many nodes are coming to C? 1. So in degree of C is 1. For B you see, how many nodes are coming towards B? From A, from C, and from B itself. So that is also considered as, so 3 in degree. How many out degree? From B to D only one edge is there, then B to itself. From B again out it is going to B itself. So that is out degree is 2. Understood, right? See here, 1 2 3 4 5, okay, then 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 3 comma 2. So from 1 to 2 I have, 1 to 4 I have, 1 to 3 I have, then 1 to itself I have, but I don't have a 5, only 3. From 3 to 2 1 I have, okay. You can either write it as nodes, or I can either use dots, thick fat dots. Then operations on relations, unions, intersection of relation. In relation also, how we will be using this union and relation. Okay, let us read the theory definition here. Why we are doing theories? Because sometimes they might just ask us in the max. Usually it happens, suddenly they'll ask of the definition. It happened the same with me in what to say, third module, third sem max M3. Luckily, I had that formula book, so I just tried to read the definitions of some formulas and understood what it means, and then I just wrote off the answers on spot preparation. It was in the examination. Okay, given the relation R1 and R2 from a set A to A and set B, from set A to a set B, okay, from A to B I have a relation, okay. The union of R1 and R2 is denoted by R1 union R2, which is defined as a relation from A to B with a property that A comma B belongs to this R1 union R2. If and only if, this triple if means if and only if A comma B belongs to R, or A comma B belongs to R2. Okay, so this ordered pair I can either belong to R1 or it can belong to R2. Why are we taking this two? It is nothing but from A to B we are deriving a relation, so it will be in the form of A comma B itself. Okay, two relations we are deriving, so it should belong either for R1 or R2. It can be and also sometimes both, it will belong to both. So the intersection of R1 and R2 is denoted by, okay, this was union, okay. If the intersection of R1 and R2 is not by R1 intersection R2, which is defined as a relation from A to B with the property that A1 comma A comma B belongs to R1 intersection R2 if and only if same way A comma B belongs to R1 and A comma B belongs same cheese. Just here a union was there. The here intersection this sign will change and here intersection is written. Here union is the definition. Same to same understood. Complement of a relation. This is theory. See here, R okay, given a relation R from set A to a set B, the complement of relation R is denoted by R complement. This upper up as R mark up this one is defined as a relation from A to B with the property that A comma B belongs to R complement. If and only if A comma B does not belongs to R. See, complement is nothing but if you are taking complement of something. Okay, so all the terms are there in R that won't be there in that complement terms. Understood, right? For example, I have universal set 1 to 9 and a set is like 2, 3. This is set A and this is the universal set. If I take complement of A, then except 2, 3, I'll write all the numbers from 1, 2, 3 won't be there. 4 to 9, like understood. That's what it means. Converse of a relation, given a relation R from set A to a set B, the converse of R is denoted by R to the power C. Okay, like that, which is defined as a relation from B to A. Okay, not A to B, from B to A with the property that A comma B belongs to R of C if and only if B comma A belongs to R. See here, converse is nothing but A to B relation is there. So converse means even from C to B, there should B to A वापस उल्टा there should be a relation. So if there is a relation from B to C, so it should satisfy the condition that B comma A belongs to that R. This happens when set A and set B has some common elements. For example, 1, 2, 3, 4 is there. Here 4, 5, 6 is there. 4 and 4 is common, right? So we might get same elements. For example, 4 comma 4 from here 4 comma 4. So we can say that relation which is converse. And see here RC they have said here RC is converse of okay A to B. I have one relation. What is that is R. Okay. Now RC is nothing but B to A. Now again if I take whole converse on this, again if I take converse on this RC to the power of C, it has got A to B. So what they are saying, RC whole C again converse double converse is equals to R itself. Okay. Then composition of a relation, consider a relation from R from a set A. Okay, just see here, and okay to a set B and a relation S from the set B to the set C. So three are there. A to B one relation is R, B to C one relation is C. And then the product or the composition of R and S is the relation from A to C. So I have from A to B, then I have from B to C is S. Then I can say that from A to C I have a relation that is nothing but composition. Okay, this will happen when A belongs to A and C belongs to C, then A comma C belongs to R composition S. Okay, A to B is R, B to C, S. A to C will is nothing but R composition dot S. If and only if there is some if and only if there is some B in capital B such that A comma B belongs to, okay, that's it. That is R composition S is equals to A comma C such that A belongs to A, C belongs to C, and there exists B belongs to B with A comma B belongs to R and B comma C belongs to S. Simple thing. Just generalizing. In general, we are telling which term is whatever is there. We can see here A comma B belongs to uh, R. Okay, that is not what relation from A to B, where A belongs to A and B belongs to B. Then from B to S, we can say that B comma C belongs to relation R, where R is a relation from B to C, like that. So note they are saying R, this thing is a subset. If R is a subset of A cross B, S is a subset of B cross C, and R composition is a subset of A cross C. Okay, what is saying, there is R relation. It is a subset of A to B, and S is a subset of B to C. Now, if you are taking R composition S, that is nothing but A to C, then there should be a subset. What is that subset? This R composition C will be a subset of A cross C. That's it. And R composition S is not equal to S composition R. Similar, same way how relation A to B is not equal to B to A, like same way you can say A union B is not equal to B, like that itself. Third, if a relation, if the R is a relation on A, then R composition R is a relation on A denoted by R square, and R composition R, again composition R is also a relation on A denoted by R cube. Okay, suppose we are taking A to A, then again this A to this A, so all are A, three sets. A is 1 2 3 1 2 3 1 2 3, like that. That means okay. Then fourth one, note 4, let R be a relation from A to B and S be a relation from B to C. Then the matrix of R comma S and R comma S and R comma S satisfy MR into MS, that is equals to M of R composition S. That's not visible. It's nothing but M of R composition S. Okay. Matrix of R square, 0 to 1 matrix of R square is equals to MR whole square, 0 to 1 matrix the whole square. Okay. And M of R power n is equals to MR to the power of whole n, where n belongs to any positive integer z. This is in this case occurs wait, please occurs or go. Okay, you understand, from this condition we are deriving result A B C D with the sets B the sets, and R S T B the relations from A to B, B to C, and C to D respectively. Then R composition whole S composition D is equals to R composition S whole composition T. Okay, so this thing remember will be helpful for us. Let no problem, let A is equals to 1 2 3 4, and let R be a relation on A defined by X relates Y if and only if Y is equals to 2X. Okay, here if I am taking 1, then Y should be 2 times of 1, that is 2. Okay, if I am taking X as 2, then R should be, Y should be 2 into 2, that is 4. Here if I take 3, it should be 6, so I cannot take that. If I am taking 4, so okay, write down R as a set of ordered pairs. Draw the diagraph of R. Determine the in degree and out degree of the vertices in the graph. Okay. No, for x and y belongs to A, x and y belongs to R if and only if y is equals to 2x. So see here, I will get only 2, like I said, 1 comma 2 and 2 comma 4. You understood, right? If I first just simply take 1, because we have first element as 1. Only one set is given, so it is nothing but A cross A, right? So if you take A cross A, then 1 comma 1 you will take first, 1 comma 2 and so on, you don't take that. If you are taking 1, this should be 2 into 1, that is 2. If you are taking 2, 2 into 2 should come here, that is 4, like that. So my relation in R is only this one. They have said draw the diagraph of R. So first, just don't draw like 1, 2, like this you might draw, then only 2 to 4 is there and you will draw like this, and don't forget to mention 3, note 3, nothing is there, just leave it as it is. Okay, how many in degrees are there? There is one out degree for A. Okay, there is one in degree for 2, and there is one in degree for 4, and one out degree from 2. Okay, so I'll write 1 2 3 4 vertices in degree out degree table. From 1, is there any in degree? No, 0. Is the out degree how many? 1 out degree is there. From 2, 1 in degree from 1, 1 out degree to 4. For 3 is nothing, 0 0. For 4 only is 1 in degree and no out degree. How will you write the matrix? Same way, since it is M of R self matrix, right? So 1 2 3 4 1 2 3 4. What is the set? 1 comma 2 and 2 comma 4. 1 comma 2 comes here and 2 comma 4 comes here. Only this place 1, remaining all will be 0. Okay, I'll explain this sum, then remaining I don't think I have to explain a lot. You can see because it's a vast portion. Let A is equals to 1 2 3 4 and 6. 5 is not there, and R be a relation on A defined by A relates B if and only if A is multiple of B. This thing we have derived the set, right? The first question in the relation. See, similarly the set one. So what is, draw the diagraph, return the in degree out degree of the vertices, write down the, say, very simple, nothing, I don't think I have to explain this. First question, then draw the diagraph. How will be the diagraph? Here it is, diagraph. It's not necessary you have to draw in this manner. It looks in, that's why I have drawn like this. You can simply draw one like this. Anyway, anyhow you have one will come extra like this. This thing you can put here, or you can put here. Anyway, that's your wish. See, these are there. So 1 to 1, one self loop. 2 to 1, 1, 2 to 2, 1 self loop, 3 to 1, 3 to 3, 1 self loop, 4 to 1, 4 to 2, 4 to 4. Okay, almost all the nodes are having one self loop. Then everything is having one out degree or in degree. 1, 2, 3, 4. How many in degrees for 1? Okay, there are 5 in degrees. See, 1 to 1 is there, 2, 3 to 1 is there, 4 to 1 is there, 6 to 1 is there. Okay, 1, 2, 3, 4, and 5, like that, find like that. Okay, same way for a set A is a set graph. The diagraph is in the figure. Okay, they have given the diagraph on a relation on A. Determine R and its associated related matrices. Now see here, A, B, C, D, E, F. Since I said only A matrix, so I'll have A, B, C, D, E, A, B, C, D, E, F. Okay, now see, A to A I have, I'll write off. A to B I have, I'll write off. Then A to C I do have, no. A to D, E, F, no. Then I'll come to B. B to A, no, I don't have. B to B I have, yes. B to C I have, no. See, they have given the direction. It is not there. That's it. So only B to B, that's it. Then C to B I have, C to E I have. C to A, D, no. C to C itself loop, no self loop. Similarly, like that, we can understand D to C it's there, D to E it's there. That's it, two places. Okay, D to C, D to E. Then E. From E, it's only going to F. Now you got the relation. Now you know that from previous problem, if there is relation, how you will put the graph A, B, C, D, E, F, A, B, C, D, E, F. Only this is our coordinates. At that place, you will write only 1, remaining all are 0. So here another question, let A be, okay, this is one sub question. Write on the, okay, see, all are very simple. Okay, so I'm just leaving it to you. Slowly I'm scrolling down. If anything you want me to explain, I can just explain it to you. Not a problem for me. See here, let me just explain this question once, because here they have asked for composition. Let A be a set 1, 2, 3, 4, B be a set W, X, Y, Z, and C be a set 5, 6, 7. Also, let R1 be a relation from A to B, and R2 be a relation from, and R2 and R3 be a relation from B to C defined by, okay, R2 and R3 we are relation from B to C. So these two relations are there. Okay. So R1 is equals to 1 comma X, 2 comma X, 3 comma Z. This is the question. Okay. This they are giving 3 comma Y, 3 comma Z. Then another relation from B to C. One from B to C I have W comma 5 X comma 6, W comma 5 X comma 6, and another W comma 5 W comma 6. Two relations from B to C, B to C. Now what they have said, find R composition R2, R1 composition R2, and R1 composition R3. So how to will I find R1 composition R2? So I have R1. So this composition, this, see here, 1 comma X, 1 comma X belongs to R1, and X comma 6 belongs to R2. Therefore 1 comma 6 belongs to R1 composition R2. Okay. Then 2 comma X belongs to R1 and X comma 6 belongs to R2. Therefore 2 comma 6 belongs to R1 composition R2. Therefore R1 composition R2 is equals to 1 comma 6 and 2 comma 6. Okay, that's it. See, now I'm not taking 3Y, 3Z, WX. Okay, why I'm not taking this 2 is nothing but I need a composition. The R1 composition R2 is nothing but from A to this. Just remember. So I'll be taking only those terms here. Now see here, 1 to X is nothing but 1 to X I have. I think you won't understand until, okay, see here. This already have done. So what is the R1 I'm taking? 1 to X I have. 1 to X I have. Then X to 6 I have. Okay, X to 6 I have. Then I can say that from 1 to 6 I have something. So this 1 to 6 is nothing but R1 composition R6. It's not only not this, it will be gone. So simple thing you have to understand is here 1 comma X is there. If there is any term starting from X and X comma Y should be there. X comma some other term should be there, and that should belong to R2 itself. Suppose there was X comma I take 4. this does not belong to R2. Okay, therefore this won't come under R common constant R2 like that. Simple thing, right? Same way, if I take R1 constant R3, this is R3. So see here, starting now here is 5 and sorry W W. So here is there any term ending with W? No, there are no terms ending with W. Then I have no terms in my what to say R1 constant R3, that is empty set, because nothing is relating. From here one thing should be there and that should go like that. Then I have to draw the M of R1. What is R1 here? 1 comma x, 2 comma x, 3 comma y, 3 comma z. So R1 is what, here you will write A, and out of you will write P. Then find the coordinates and fill off. Second question, third question, fourth question, and now see. Okay, how you will find for R1 constant R2? So you got here, you calculated, right? So you wrote here R1 constant R2 is 1 comma 6, 2 comma 6. So according to that, you will write the what to say set. So see here how you will select the rows and columns number thing. Since R1 consists R2 is nothing but from A to C, so down you will have A left side, and in column place you will have C. Nothing else. That's it. Then similarly this question they have asked R composition. Then again R composition S. First you have to find this thing. Then again you have to take it composition like this. Nothing is simple, right? That only that thing you have to take. Okay, see here R2S. So from this you can figure out how many R constants. I have one element, two element, three element, four element. So my R composition S will have four elements. 1 2 1, 1 2 2, 1 2 3. 1 comma 4. R composition S is equals to 1 2 4. Okay, 1 2 4. Then 2 2 1, 2 2 1. Then 3 2 4. Why am I not taking 1 2 4? It's already taken. Oh, okay. See here 1 to 1, then 1 to 4. 1 to 2, then 1 to 4. Both are same. So instead I cannot write two times. So I'm just taking 1 to 4. Okay, that's it. Then S composition R. So first what I'll do, I'll write S. Then I'll write what to say composite R. I'll write nothing but see here how many sets then R and S they have given, right? From this two I can write set A, same thing. So here also same thing, and here also same thing. S composition R is nothing but uh, so suppose it is A comma B. This will be B comma A should belongs to S. Sorry, R. Here A comma B should belongs to R also, S also. Here B comma A should belong to R and S. How that will come? So this is first if I write R to S. So first of all I'll take A to A is R, and again this A to A is S. Now what I'm taking, this is R composition S. If I take whole like this, okay. Now this like this. If I go, this is from S to what to say R. This is S to R. S to R I'll write as like this. Then from this A to A, that is also one thing. So like this, if I take whole go, that will be S composition R. Above one is nothing but this one, R composition S. Okay, where it go like that. S composition R also we can simply take off. They have given in the question S is there, right? 3 to 1. So for first write 3 to 1. So ending is 1. Do you have anything starting with 1? Yeah, 1 to 1. So I can simply write 3 to 1, then 1 to 1. Same way 3 to 1, 1 to 2. Similarly, I have here 1 to 4. Just draw this diagram first. Then you'll automatically get. So if there is a like long connection like this, from here directly it is going, then that will be your actual required thing. Similarly, now you have this and this set. So here only 1 2 3 is there, here 1 and 2 is there. Now they are asking R composition, whole composition of R composition S. So how this will be? So you have to write 1 comma 1, 1 comma 2, 2 comma 3, 3 comma 4 composition this. So what you do, just write these four sets here, 1 2 3 4. Then second set you have to write like this, 1 4 2 1 3 4. Just understand. So here 1 comma 1 starting. So here what is ending, and it has to start from here. So 1 comma, it is ending with 1, and here it is starting also 1 comma 4. I'll write off 1 comma 2. So it should end with 2. Ending with 2, anything starting with 2, yeah. So here 1. So I'll write 1 comma 1. Then 2 comma 3, ending with 3. Anything starting with 3, yes, which is 3 comma 4. So I'll write 2 comma 4. Then here ending with 4, is there anything starting with 4? No, nothing. So nothing. That is 3 things. Okay. Then R composition, S composition, R. What is R in the form giving like that? Okay. I hope I have explained properly. Very simple, man. You don't have to break your head. You will understand this, right? Similarly, R square is nothing but R composition R from the given definition. Okay. So 1 comma 1, ending with 1. Anything starting with 1? Yes. So I'll write 1 comma 1. 1 comma 2, ending with 2. Anything starting with 2? Yes. Then so I'll write 1 comma 2, right? Starting with 2. So I'll write 1 comma 3. Here I have another 1 comma 1 ending with 1, but here also it is starting with 1. Okay, two things are there. One ending with 1 here, starting with 2 are there. So I'll write first 1 comma 1, then I'll write 1 comma 2. Then here 2 comma 3. Anything starting from 3, yes, one thing is there. So 2 comma 4 I'll write off. Then 3 comma 4 ending with 4. Anything starting with 4, no, nothing. Same way S square done, right? So here anything they are saying to verify. This, see the question, read properly. They are asking to verify. So you have to find each individual properly. Find first R square. R square is nothing but R composition R. Okay, this is R composition R. You have to find the relation, that set. Okay, that is whatever you get that thing, write the matrix. Here A values will be there, here A value will be there, here also 1 2 3 4 1 2 3 4. Whatever the coordinates you are getting in this R constant R, according to that plot the graph and write it off. Then you have to take M constant R. So plot a graph of this coordinates. Then take whole square, nothing but that matrix into that matrix. See here, MR is nothing but this matrix. For MR whole square, you have to multiply this into this, like they have done here. And then you have to just a simple matrix, first row with first column. Here all are 0, so you will get this first letter will be 0. Then this whole thing into this thing. All the complete value if you add, that will be your this multiplication. So 0 into 0 plus 1 into 0 plus 1 into 1 plus 0 into 0, that is 1. Okay, like that. Now see here, this is my MR square, and MR the whole square, MR square, and then MR cube is like this. MR cube is what is how we will write MR cube, that is R composition of R composition R. Find this whatever you get on the diagraph like that. Now see, in question whatever they have asked, now you can put our answer. Okay, MR square is equals to MR the whole square, MR cube is equals to MR the whole cube, MR square MR cube. Yeah, MR the whole square can be written as M of R into M of R. Okay, M of R square is nothing but you are drawing the graph of R comes done. The diagram of the select two relations R and S on the set A. You know, see this thing are simple. Okay, from here I am just skipping. If any question you need, you can let me know. So properties and relation. So many things are there with the problem. Okay. So first let me say this very simple topic, irreflexive. Reflexive means now I have set 1 2 3. What is the meaning of reflexive? Means there should be 1 comma 1 2 comma 2 3 comma 3, then it is reflexive. Do I have so I don't have 1 comma 1 itself, so there itself directly I can say it is irreflexive. Symmetric means what? If I have 1 comma 2, then I should also have a pair 2 comma 1. I have 1 comma 2, I have 2 comma 1, yes. If I have 1 comma 3, I have 3 comma 1, yes, it is symmetric. Transitive means suppose I have 1 comma 2, then I should also have a set, and then I have a set 2 comma 3. Okay, then I should have a set 1 comma 3. Understood, right? If I have a comma b one set, then I have b comma c one set, then I should have c a comma c also should be there in that what to say set. Okay, so they are given R1 is equals to 1 comma 2, 2 comma 1, 3, 1 comma 3, or 3 comma 4. So I have to write whether it is written the nature of the relations on A. What are the natures? Either it is reflexive or irreflexive, symmetric or asymmetric, transitive or non-transitive. So from this given thing, I can say that it is irreflexive because 1 comma 1, 2 comma 2, 3 comma 3, either 3 also not there. It is symmetric, yes, here. Is it transitive? So I have 1 comma 2, then I have 2 comma 1. I should have 1 comma 1. Do I have 1 comma 1? No, I don't have 1 comma. So it is not transitive. If see, like any one is not there. For example, that in Max first module and in AI subject, for all there exists. See, it's like for all condition. If any one condition is false, then complete whole thing will be false. So if you find only one thing is not there, then you can directly see that whole thing is not transitive. Now R2, 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there, then 2 comma 3 is there. Okay. Now see here, is it reflexive? Yeah, because all 1 comma 1, 2 comma 2, 3 comma 3 is there. Is it transitive? So if transitive, see, I have 1 comma 1, then I don't have another. So I can take 1 comma 1 again. 1 comma 1 I have again 1 comma 1. I can use 1 comma 1 again. So 1 comma 1 is there. This is A, this is B, this is B, this is C. Again I can consider 1 comma 1. That is nothing but C A. So it's there. Now I have here 2 comma 3, 2 2, then 2 3, A B B C. So I have to have 2 comma 3. I already have 2 comma 3. I can use it again. See, usually most of the people get confused here. It's nothing but you can use any pair again and again. You can use 100 times also if you want. That's the simple thing. See, if I'm simply I'm considering 2 comma 2 is there and 2 comma 3 is there. 2 comma 2, 2 comma 3. This is A, this is B, this is B here, and this is C. So A, what will be A comma C? That is 2 comma 3. Okay, it is already there here, right? It's not like if I take this one set, then it's already gone. If I take like popping out, it's not like that. Okay, don't consider that. This is asymmetric. Why? Because I have 2 comma 3, but I don't have 3 comma 2. Only because I don't have 3 comma 2, I won't be having what to say. That's why it's asymmetric. Suppose it had 3 comma 2. Okay, so then it will be all three things. Then here I have 1 comma 1, 2 comma 2, 3 comma 3. Remember always, if there is a pairs in a set relation which is like 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4, then it satisfies all the natures. It is done. How means, see, I can take 1 comma 1. One time I took. I'll take it again one time. 1 comma 1. Now here I will say this is A, this is B, this is C, this is D. Now, oh sorry, this is B, this is C, right? A comma B, B comma C. And now A comma C is there, right? Again 1 comma 1, that is. I will consider that same pair again. I am having that like that it is. Simple thing. Similarly, you see this, I pause it, try to solve it out. Then, if A is equals to 1, 2, 3, 4, and R be a relation on A, give an example of a relation for each of the following. So, I have a set A 1, 2, 3, 4. So, I have to now form a relation such that first thing, it is reflexive, it is symmetric, but it is not transitive. If it has to be symmetric, then I'll simply write off 1 comma 1, 2 comma 2, okay, 3 comma 3, 4 comma 4. I have proved the reflection. If it is it has to be symmetric. Since it is saying symmetric, you don't have to go and write all this 1 2 2 1 1 3 3 1 1 4 4 1. If you do like that, it will lead to the what to say proving this transitive thing. It should not be transitive. If see now I can take if I take 1 2, okay, 1 comma 1 is there, 1 comma 2 is there, A B B C, then okay, 1 comma 1, 1 comma 2, this A comma B, this is B comma C, then 1 comma C. So I cannot take that. Why? Because it will become transitive. So don't consider this set here. Okay. Okay, anyways, if it has to be transitive, all the things should be transitive, all the elements should be transitive. So it's not a problem. Okay. What I said now, like for all condition, if any one condition is true, even though some conditions are true here, but if one condition is false, then whole thing will become false. Okay. Though here I have this and this thing satisfying transitive property, but if we try to see, like see, I have here 2 comma 2, 2 comma 1. Okay. This is also for satisfying the transitive property. Then 2 comma 3 I have. I don't have here 3 comma 2. Oh, sorry, I have here. So 3 comma 2. 3 comma 2, 2 comma 3, I have 3 comma 3. Okay, so this is what to say. Now I have 4 comma 4. I don't have, I have A comma B, but I don't have B comma C itself. Okay, or A comma C here. Or see, but I can take this root. So see here, actually they have written here. This is it is satisfying all the this one. Okay, okay, actually here what you can do. Just try to think and see what you can do. You can take one set in such a way that uh, 1 2 see 1 to 2 is already not there. I can take 1 comma 4. Okay, if I take 1 comma 4, I have to take 4. If I okay. Let me just think. Anyhow, this time is being wasted, right? Reflexive. See, in reflexive, suppose I'm not giving this right. I have only written 1, 1, 2, 2, 3, 3, but I'm not writing 4, 4. Then what will happen? It will be irreflexive because all the elements in the set should have that reflexive property. Okay, but not transitive. So, somewhere we can, I think, do here. 2 comma 2. Oh yeah, see here. I have 2 comma 2. Then I have 3 comma, okay, 2, 2 will become again, then 2 comma 2 and 2 comma 3, then again 2 comma 3 I have 3 comma 3, 3 comma 2, 3 comma 2 I have 4 comma 4. Okay, see, I think this thing, whole thing is satisfying it is also transitive. I have to do one change here. See, now reflexive and transitive, but not symmetric. So I can simply write 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. Then I will write 1 comma 2. That's it. Now see here from these two things 1 comma 1, A comma B, B comma C. Then A comma C I have 1 2. So done. Here I have to do something here. Okay. So in such a way that it should not be transitive. Or it's A comma B should be there and B comma C should be there, but A comma C should not be there. So for that to happen, there should be a set in such a way that B comma C should not C should not be equal to B. Okay, we have to write in such a way that A comma B is there. B comma C, if you take here, C should not be equal to same thing. So if I take 1 comma 2, so I have to take 2 comma 3. Okay, so such that 1 comma 3 is not a, oh, I can take that, right? 1 comma 2, see here, done. I have 1 comma 2 here and 2 comma 3 here. Do I have 1 comma 3? No. Because of these two things, okay, just ignore this. I can say that it is not transitive. Yeah, it's nice. It's correct, man. Simply breaking my head. Then I will erase this thing. Okay, so they are saying symmetric and transitive but not reflexive. So you can simply write, you can finish in two things. You can write 1 comma 1, okay, then 1 comma 2, then 2 comma 1. That's it. And you can simply write this one thing also and leave off, or else you can just write 3 also like this and leave off. Simple. See, if you write only 1 comma 1, okay, it will satisfy that 1 comma 1. But yeah, if you take only one, yeah, because since 2 3 4 is in a set, only 1 comma 1 is cannot be stated as reflexive because the other elements reflexes are not there. So this thing, see, symmetric 1 comma 1 is there, then again 1 comma 1 is also A comma B, B comma C is there. Transitive, I will consider this 3 times. You understood, right? Same way, let A is equals to 1 2 3 4 and in relation 1 comma 1 to 1 comma 2, 2 comma 1, 2 comma 2, 3 comma 4, 4 comma 3, so on it is given. And be a relation on A, verify that R is equivalence relation. Equivalence relation means To verify R is equal, we have to show that R is reflexive. All three conditions should be there. So now see here, for R to be reflexive, 1 comma 1, 2 comma 2, 3 comma 3, and 4 comma 4 should be there. Here 1 comma 1, 2 comma 2, 3 comma 3, and 4 comma 4 should be there. For it to be reflexive, if I have 1 comma 2, then 2 comma 1 should be there. If I have 3 comma 4, then 4 comma 3 should also be there. Okay, so I can say that it is reflexive. For it to be transitive, now I have to write again. I have 1 comma 2, then I have 2 comma 1, then I should have 1 comma 1. From this 2, I have 1 comma 1. Same way, I have 2 comma 1, 1 comma 2, same it will, that will 2 comma 2 should be there. I'll take now this 2. 2 comma 1, 1 comma 2, okay, then 2 comma 2 should be there. Similarly, okay, nothing else I can take here. Yeah, then 3 comma 4 and 4 comma 3. 3 comma 3 should be there. Yeah, it is there. 4 comma 3, 3 comma 3, then 4 comma 3 should be there. Yeah, it is there. 3 comma 3 and 4 comma 4. No, this thing too I cannot take. 3 comma 3 and 3 comma 4. So 3 comma 4 should be there. Yeah. So it is reflected. So that's what. Just write all the possible transitive relation, excluding what to say, reflexive term. We can simply prove that it is transitive. Same way, okay, let A is equals to 1, 2, 3, 4, so on up to 12. On this set, define the relation R by x comma y belongs to R if and only if x minus y is a multiple of 5. Okay, I have to select two terms. If I subtract x with y, it should be multiple of 5. So for that to happen, it should be either 0, the sum x minus y should be equal to 0, 5, 10. Okay, that's it. I cannot take more n terms. I cannot take 15 because it is subtraction, right? So, oh, I can take, right, 12 minus, no, I cannot take. So, the highest term itself is 12. So, if I consider y or x as 12, so I cannot do anything. So, only this. It should be either 0, 5 or 1. So, let us see. Now, for any x belongs to A, we have x minus x equals to 0 is a multiple of 5. Therefore, 0A is equals to 5 into 0, that is x comma x belongs to R. So, I can take 1 comma 1, 1 comma 2 comma 2, 3 comma 3, 4 comma 4, 5 comma 5, so on to 12 comma. So, how many terms there? So, 12 terms I have already got here. So, I have to just prove that it is equivalence relation right now. It is a so 0, 5, and now see each term x comma x I am taking. So each sum by itself I am taking, that is nothing but x minus x is, instead of x I am taking x 1, instead of y also I am taking x, that is 1. So all terms are 0. So all terms are 0 is divisible by 5. Then like this 0 by 5. Okay, done. Then second thing, for any x comma y belongs to A, if x comma y belongs to R, then y uh, okay, we are saying x minus y belongs to R, that is x minus y is equals to 5k. We are just writing for some integer k. Then we have to prove that y comma x should be there. That is nothing but y minus x should be equals to 5k. I have to prove in such a way. Okay, so let me take okay, y minus x is equals to minus 5. So I'm just multiplying minus for this. Okay, my y minus x is equals to 5 into minus k, minus of k. So that now what is this? See, this is minus k. Now what I did, I just multiply with minus here. I got y minus x is equals to 5 into some integer, that is minus k. Now since this minus k is multiple of 5, okay, it is a multiple of 5, right? Then x, this x comma y belongs to R. Simple thing. What they done? See, 5 should not be minus. I just grouped this minus with k. So minus 5k was there, which is also equals to 5 into minus k. Okay, that's it. Then for any x comma y comma z belongs to A, if x comma y belongs to R and y comma z belongs to R, then there should be a x comma z which belongs to R, which means x minus y is equals to 5 into k1. Then y minus z is equals to 5 into k2 for some integers k1 and k2. Therefore, x minus z is equals to x minus y minus z minus y. Okay, so x minus y. uh, y minus z, so it should be x minus z is equals to something. If I take x minus z, so here I have x minus y. So how this equation comes is nothing but, see, x minus z I have to do. So I'll have x minus z. So I'm just adding y and subtracting y. So here I have minus. So what I'm doing? So here I'll group this x minus y here, then plus y minus z. Okay, so plus y minus z. So what I'll do? Minus of z minus y. So if I multiply this minus sign, so I'll have minus z and plus y minus z, right? Same thing. Now here what I'm doing? So what I'll do? I'll multiply this. Okay, same thing. I can simply do adding and subtracting. So I simply double step it is. So x minus y as it is, plus y and minus z as it is. So I'll write this as it is. So I have this value already. I have given, right. So 5k1 and 5k2. 5k1 plus 5k2. So I'll take 5 common. Then k1 plus k2. So it is a multiple of 5. Therefore x comma z belongs to R and R is transitive also. Like that we have proof. Same way, if A1 union A2 union A3, okay, A is equals to this, then where A1 is equals to 1 comma 2, A2 is equals to 2 comma 3 comma 4, and A3 is equals to 5. Define the relation R on A by X Ry if and only if X and Y are in the same set AI, where I is equals to 1 comma 2 comma 3. Is R an equivalence relation? They have asked. Now see here, A is equals to A union A2 union A3. So what I have to do, among these three sets I have to union. So I will write all the numbers which is repeating. I won't write. So 1, 2, 3, 4, 5. Now I have to consider a relation X relates Y if and only if X and Y are in the same set AI, where I is equals to 1, 2, 3, A1, A2, A3. So now here I have taken relation 1, 1, 1, 2. Okay, where is that? 1, 1, 1, 2. 1 comma. So A1 cross A1. 1 comma 1, 1 comma 2. Then what has this? Okay, then I have 1 comma 1, 1 comma 2. Then I have again, if I do A1 cross A2, I have 1 comma 2. Already I had 1 comma 2 from A1 cross A1, so I won't take that. So I'll write 1 comma 2, 1 comma 3, 1 comma 4. So here 1 comma 1, 1 comma 2. So this is 2 comma 1, 2 comma 2. Then 2 comma 3, 2 comma 4. I'll have 5 comma 5 also. Then 2 comma 5 is there. It's not there. Okay, I think it is nothing but A1 intersection A1. A1 intersection A1. Then A2 intersection A2. That's what this sentence mean, I guess. Okay. Then A3 intersection A3, like that. I'll do like this and I'll write off. So I will get this. This 2 is from A1 intersection. Then till here. That is what to say, from A2 intersection 2. Then this is A3 intersection A3. So I hope you have understood the problem. Okay. Actually, I had to pause here suddenly. Then I have just started recording again. So in this question, whatever they have asked here, if I see here, what I said is, so it is nothing but A1 union A2 union A3. Right. So this relation R, how they have they define the relation R on A by A relates Y if and only if X and Y are in the same set. That is, AI is equals to set is A of I, where I is equals to 1, 2, and 3. Is R an equivalence? So what I'm doing, first A cross A, A1 cross A1, A2 cross A2, A3 cross A3. This 2 is for a1 cross a1. This whole thing for 2 comma 2, 2 comma 3, 2 comma 4, then 3 comma 2, 3 comma 3, 3 comma 4, 4 comma 2, like that. Now I have to say if it is reflexive or not. So I have 1 1, 2 2, 3 3, 4 4. I have, yeah, and even 5 comma 5. Yes, it is reflexive. So second thing, is it symmetric? I have to find. Whenever a comma b belongs to R and b comma a belongs to R, for all a comma b belongs to a, that is symmetric. How? Let us see. 1 comma 1 is here, 1 comma. So 1 comma 2, 2 comma 1 is here. Okay, 2 comma 2 replaces, so already it is self symmetric. 2 comma 3 is there. I have to check whether 3 comma 2 is there. Yeah, it is there. 2 comma 4 is there. I have to check whether 4 comma 2 is there. Yes, it is there. Then I'll check 3 comma 2, 2 comma 3, done. Then 3 comma 4, 4 comma 3, it is there. 4 comma 2, 2 comma 4, it is there. Yeah, it is symmetric for all a comma b. B comma a is also belonging to R. Now whether it is transitive or not. So for it to be transitive, it should be in the form that a comma b should belongs to R and b comma a also should belongs to this R, and there should exist a pair such that a comma c should also belong to R. Okay, that thing I have to now find here. So see here, uh, I have here 1 comma 2, then I have 2 comma 3. Okay, 1 comma 2, 2 comma 3. Do I have 1 comma 3 now? I don't have now, so it is not transitive. Just try to find the any one condition which it is where it is not equal, and then simply you can say it is not transitive. Done. So they will sometimes they might, I think they might just ask you like prove it, it is equivalence. I feel if the paper is hard, they'll usually give it is not equivalence. This it won't be transitive, because this transitive part itself is the trickiest part to find out. But if the paper is easy, then this should be easy. For a fixed integer n greater than 1, prove that the relation congruent modulo n, what is that? Is an equivalence relation on the set of all integers z. For any a comma b belongs to z, a is a congruent to b modulo n. Okay, it is congruent. Okay, Gruent. Okay, spelling mistake. So a triple line is denoting congruent b mod n. If a minus b, okay, so for a fixed integer n greater than 1, so n greater than, so I cannot take n as 0 or 1. So it will start from 2, so on. Prove that the relation in congruent modulo n is a equivalence relation on the set of all integers z. For any pair a comma b belongs to z, a is congruent to b modulo n. We are taking assuming like this. If a minus b is a multiple of n, that is a minus b is equals to k into n, n into some integer k. Okay, for some k belongs to z, let R be a relation on z defined by a relates b if and only if a is congruent to b mod n. Okay, now first I have to prove this congruent modulo n. Now first what I'll take, I'll consider both a and b as equal. So a minus a is equals to 0, which is equals to 0 into n, which is equals to a congruent a into mod n. Therefore a relates a. A is reflexive. So again I have to show that if it A is reflexive, what to say, symmetric or congruent. So here since A relates B, A is congruent to P mod n. Therefore A minus B is equals to K into n. So B minus A, if I take that, is relates to minus K into n. Again same multiple of n. Then B is congruent to A mod n. B relates A like that. Then when when I have, thus whenever A relates A, B relates A for all A comma B belongs like that. Just see this question by yourself, and because I have already solved one question like this previous, right? Just simply here mod n they are giving us. Don't get confused by that. Simply you will write this as it is. You will prove the congruency. How? For reflexive, A congruent A into mod n should be there. For transitive, if you have A congruent B mod n, then you should also have B congruent A mod n. For transitive, if you have A congruent B mod n and you also have B congruent A mod n, A mod B congruent C mod n, then you should also have A congruent C mod n. Okay, like that you have to prove. Same way they are taking. Simply first take A minus B, then take B minus C, then do A minus C, which is equals to k1n plus k2n. How k1n plus k2n is? I am just adding and subtracting b. A plus b minus b, then here minus c. So I'll pair a minus b, then I'll pair b minus c. A minus b is k1n, b minus is k2n. I'll take n common, k1 plus k2. So I have this as multiple of n. Okay, it is proving. For the equalization R 1 comma 1 comma 2. Okay. Okay, define on the set A, define the what is this, partitions induced. The equivalence classes of the elements of A with respect to R are 1. For 1 I have only 1 comma 2. For 2 I have 1 comma 2. For 3 I have 3 comma 4. For 4 I have 3 comma 4. Of these only 1 and 3 are distinct. The equivalence classes are, okay, so the equivalence classes among these are, okay. For 1, what I can take the equivalence class for 1. Okay, so now I can take this as uh, okay, 1 and 3 are distinct. So therefore the partitions 1 comma 3 is 1 comma 2 1 comma 3. It is a partition of the given A induced by R. Have they given something else for this? What kind of question is this? 1 second. So they have just induced it over here and taken. So only this much is the answer. Okay, I'll try to solve this question in some other place because I didn't prepare for this kind of question. Usually what is happening, instead of this, they are not writing the reflexive term, but writing one extra term in which it can satisfy that equivalence property, like that, something like that it is. Then find the partitions of A induced by R given 1, 2, 3, 4, 5, 6, 7, 8, so on up to 12. So here R is equals to x y belongs to R if and only if x minus y is a multiple of 5. Solution, give partitions into the argument. Okay, that is R is equals to 6 comma 1. So now see here 6 comma 1 I can write in such a way that 6 comma 1 is what, 5. 7 comma 2 is 5. So here simple, just keep adding 1 1 on each sum until 12. So 6, 7, 8, 9, 10, 11, 12. Then here 1 was there, so you keep adding 1, 2, 3, 4, 5, 6, 7. And then here keep reducing one term and again start with 1. Oh, sorry, that's it, right? Till here, same thing. Then 11 comma 1, 12 comma 2, 1 comma 6. Then what you have to do? Same thing. Uh, 11 comma 1. Okay, 11 comma 10. Okay, so these terms here gives you what to say, 5. Answer as 5. 6 minus 1. Okay, here they have also taken 2 comma 7, which is 2 minus 7, which is nothing but minus 5. They are also taking minus terms. So which, how you have written this? Just write ulta of that. So you can just write 7 comma 12. Okay, if you write 7 comma 12 also, you will get. See here, how whatever is there, you just write ulta. Then what you can do? So you can start like, so here 12 is there, minus 2. Here 11 is there, minus 1. Okay, then 10. You cannot take 10 minus 0. So 9 minus also you cannot take. So you will take 11 minus 1 is 10, 12 minus 2 is, and then again you will start writing this ulta. 1 comma 6, 2 comma 7, 3 comma 8, 4 comma 9, 5 comma 10, 6 comma 11, 12 comma 7. Then again I have this also, I'll write ulta. I took 11 comma 6, 12 comma 2, then I'll take 1 comma 11, 2 comma 11. Okay. Here I can also take all the sets from what to say, reflexive terms 1 1 2 2 3 3 4 4. Why? Because all those 12 times will give us 0. So 0 divides 5, minus 5 is divisible by 5, 5 is divisible by 5, okay, 10 is divisible by 5. So among these numbers I have to select a pair such that x minus 5 will give me either 0 or minus 5 plus 5 or 10. Basically you have to just find this and this, okay. You can also find for minus 10 also, okay. If you just find for only 10 and just write the inverse of this number and you can continue. Okay, equivalence classes are 1 is equals to 1 comma 6 comma 5. 1 6 5. I think the equivalence classes. So it simply means that whatever the pre-image was, so 1 is there, wherever 1 is there, before that what term is there? You know, here I have 1, here I have 6. So before 1, here I have 1, before that 11. That's it. Remaining no place I have 1. So that's why I'm writing 1 6 11 here, I guess. Okay. Then 2. Second term 2 is there, so 2 will come. Second term 2, so 7 will come. 2 2 2 2 2 2 here. 2 is there, 2 will come. So 2 7 12. Okay, just have 3 wherever 3 is pre-image. So for 3 will be there obviously. For 4 also will be there. For 5 will be there. Where 3 is there? Okay, here 3 is there. Before that 8 is there. Remaining no places. Same way. Where 4 is there. Here 9 is there. Where 5 is there, 10 is there. Okay. Equivalence classes we wrote out. All these classes are distinct. If I start taking from 6, what to say? See here you can observe that from here till here any number has not repeated. So 1, 2, 3, here 4, 5, 6, 7, 8, 9, 10, everything has been considered. So remaining, if I try to find for 6, 7, and 10, the repeated numbers will be appearing. All the classes are distinct, thus this is the partition of A induced. So similarly, I think I can say here, okay, for induced. So here also I can just say now, for 1, here 1 is there, before that what 1 is there, here 1 is there, before that what 2 is there, so 1 comma 2. For 2, before 2 1 is there, here before 2 2 is there, so 1 comma 2. For 3, second term, where is second term 3, here 2 times, so before 3 3 is there, before 3 4 is there, so 3 comma 4. For 4, where is last 4, here 4 is there, before 4 what 3 is there, before 4 what 4 is there, okay. So what will be the partition? So in this which is distinct, we can take only first this one term distinct. So the partition is nothing but 1 comma 3. Partition of 1 comma 3 is but 1 comma 2 comma 3 comma 4. Same way here, if you have to do partitions of all these three things, so you will write this set comma this set comma this set. That's what union you have to do. If you do union, you will get 1 to 12 everything. Just see here again. This I won't solve. You can simply see and solve it by yourself. Okay. I'll move on to this partial orders, this Hasse diagrams and partial orders kind of question. Okay, so Hasse diagrams we have to start now. I'll do this in next lecture because it's already 1 a.m. of the midnight and I have to sleep.
Can I please ask you to subscribe? That's all we want, man. Just press subscribe.